Hi everyone, thanks for joining. I'm Nitish, a PhD student at University of Massachusetts Amherst. The title of my today's talk is On the Analysis of Spatially Constrained Power of Two Choice Policies. This is a joint work with my collaborators from Raytheon Behavion, Army Research Lab, and Imperial College London. So here is a brief outline of my today's talk. First, I'll discuss behind the motivation of this work, followed by various resource allocation policies available for users and servers that are distributed on two-dimensional Euclidean plane. And then I'll briefly discuss about few performance matrices associated with these allocation policies, such as load and request distance. Followed by, I'll introduce two new policies, such as dPOT and KSPOT, as we call it, and few simulation results associated with it. And lastly, I'll discuss about a few future works. So, so what basically we consider here is a collection of smart devices, servers, and end users that are geographically distributed on a two-dimensional Euclidean plane. And few examples include wireless sensor networks and data center networks and vehicular ad hoc networks. So one important aspect here is that these users or applications and resources or servers in these distributed service networks, they're basically spatially distributed on an Euclidean plane. So these spatial distribution of users and resources play an important role on determining the performance of the overall system. So that brings us down to the following set of questions. So basically, first, how should we allocate users or applications to servers or resources in a distributed service network? And then the second question being, what sort of performance matrices should be considered to evaluate these allocation policies, basically? So one, we can try to minimize the load. So here, load is nothing but the number of users that are allocated to a server. And second, we can try to minimize the request distance, which is nothing but the distance between a user and its allocated server. So with respect to the load part, basically, there are a few policies that have already been proposed in the literature, and they're quite popular, and which is basically the power of two choice policies. So consider this setup here. The red nodes are basically the servers denoted by the server set S, and the blue nodes are the users denoted by the set U. And each server here has an instantaneous load value. And now what power of two policy does basically is, so in a power of two choice policy, basically you have the entire server set S as your candidate set of servers. And from the candidate set of servers, you choose two servers uniformly at random, as shown here. And once you choose two servers, then you get allocated to the one which has the least load. For example, here for user U, this server on top right has a load value 4, which is less compared to this load value 5 here. So that's why U gets allocated to the top right server here. So this is what basically power of two choice policy is. Now, what we are going to propose here in this work is a variation of this power of two choice policy. So basically we propose a spatial counterpart of this power of two choice policy, which we define as follows. So again, the setup remains the same. And for a particular user U, what you do is you go to the two nearest servers. So now your candidate set of servers is drastically reduced to 2, basically, which is nothing but the two closest server to user U. And from that candidate server, there's no sampling involved here. So the sampled servers are basically these two candidate servers, and then you gets allocated to the one which has the least load. So here, for example, this U gets allocated to the server which has the load value 6, which is the least one. So this is what we define the spatial power of two choice policy is. So what we see from the literature that the maximum asymptotic load behavior for various non-spatial policies, load balancing policies, for example, power of two that we discussed here, is the maximum asymptotic load is order of log mod s, where mod s is the total number of servers. There's another policy we call it as power of one, which is nothing but randomly allocate a server to a particular user. That has a maximum asymptotic load of order of log modest divided by log modest. Again, modest here is the total number of servers. And here you can see an exponential improvement over the power of one policy, basically, when you go to the power of two policy domain with respect to load. So this exponential improvement is also popularly known as power of two benefits, or POT benefits in short. So what we have here basically is the question that we propose here is, does the SPOT policy, the spatial power of two policy, provide you these load improvement or POT benefits basically? So the simple answer is no. What we're able to show in this work is that SPOT does not provide you POT benefits. And we are also able to show that when users and servers are basically placed uniformly at random on a 2D Euclidean plane, the SPOT policy is, the load associated with the SPOT policy is nothing but omega of log modest divided by log modest. If you observe here, the PO or the random allocation basically gives you this load behavior. So what we are claiming here is if you adopt a SPOT policy, then you're no better than the random policy or the power of one policy. So basically, we do not get power of two benefits. Another thing that we explore here is basically there is an inherent trade-off between these two performance matrices, load and request distance. So what we consider here is basically four policies, and the new one is the SPO, or known as spatial power of one, where each user is allocated to its nearest server. So the setting here is basically we have 10,000 number of users and servers distributed uniformly at random on a 1x1 square. And the left plot here, basically we have maximum load. The left bar plot here is the maximum load for all these four policies. And the right plot here is the average request distance for these four policies. And what we observe here is basically the POT policy here basically performs best with respect to load. So lower the better here. And also here lower the better. But POT performs worst with respect to request distance across all four policies. Another observation here is that SPOT performs worse than power of one with respect to load, as you can see here. So this is inconsistent with the results that we get from our previous theorem. So basically we have a trade-off here between load and request distance. So that brings us down to the following question. Can we get better of both the worlds? That is a load behavior like POT and a request distance profile like SPOT. The answer is yes, but we need to take care of these two things basically. First, the sampling associated with the new policy should be random to reduce load. That is, if you remember, SPOT does not have a random sampling. There's no sampling actually in SPOT policy. And the second thing is the sampling should be distance based to reduce request distance, because if you remember, POT is distance oblivious. So with that, we propose these two new policies, dPOT and KSPOT as we call it. dPOT is distance-based POT, which is nothing but, in this case, each user have this entire server set as its candidate set, and then it samples two servers uniformly. Instead of uniformly at random, it samples with a probability, which is proportional to 1 over d squared, where d is the distance between that server and the concerned user, and then it gets allocated to server with the least load. Another policy that we propose is KSPOT, which is in which each user forms a candidate set of size k, which consists of the k nearest server to that particular user. And from that candidate set of size k, it samples two servers uniformly at random and then gets allocated the one which has the least load. So with these two policies, we have few simulation results. So what we observe is that dPOT achieves POT-like load behavior. So here we have a setting of 50,000 users and servers distributed uniformly at random on a 1x1 square. And we show the probability, the PDF basically of the server load for dPOT on the left figure here, and for the PDF for POT on the right figure here. So as you can see, they have an identical maximum load value, and also the PDF is almost same for these two policies. So that's good. We are getting POT-like load behavior for dPOT. Another thing we see here is dPOT achieves pretty low request distance. So as you can see here, the PDF for the request distance is towards the left for dPOT and as compared to the POT. And the dotted line here is the expected request distance. So the right figure here is here for POT, and it has higher expected request distance compared to the dPOT policy. We also perform simulations for KSPOT policy. So here we have on the left plot, we have average maximum load as a function of number of servers. On the right plot, we have average request distance as a function of number of servers. Colors represent various policies. The orange curve here is basically the KSPOT policy. On the left, you can see it is closer to POT, which is the green curve here. So with respect to maximum load, it is closer to POT. And here on the right, with respect to average request distance, it is away from POT. So it's quite away from the POT, closer to the SPOT policy here with respect to the average request distance behavior. So with this, what we would like to consider in future is that instead of static setting, we want to consider a dynamic arrival of users. It can be mapped to the classical supermarket model actually. And also we want to consider various topologies associated with the servers. Instead of a 2D placement, we need to consider a more general graph-based server placement and then evaluate these 6 policies basically. That would be our future work. And with this, I'm open to questions. Thank you.